Our next experiment is the determination of speed of sound, measurement of speed of sound in the lab. And we use a device called a resonance column. So the resonance column is used to study. But before you study this one, you need to know what is resonance. That's the first thing. So let's learn about resonance. Now, in one of the chapters, chapter 6 maybe, you will definitely see this thing called vibrations, waves, and stuff like that, right? So resonance is definitely there. So vibration. You can have vibrations that are free vibrations, like a pendulum. A swing is a free vibration, right? Natural frequency. So what happens is in a pendulum or a swing, when it swings left and right, it'll maintain a timing, which means it has a frequency. It goes a certain number of times per second. And that's called the natural frequency. Every pendulum or every swing has a natural frequency. Every object has a natural frequency of vibration. If I hit this, it's vibrating. If I hit anything, it will end up vibrating, right? And that is the natural frequency. If I hit this, it's going to vibrate. That is the natural frequency of that. Everything that you see in this room has a natural frequency of vibration. That projector will have its own natural frequency of vibration. And then there's something called forced frequency. Forced frequency. What's forced frequency? You can force any object to go at a frequency that you desire. You can make any object go according to your wish. How? Okay, this is a swing, it has its own frequency, but if I hold the swing in my hand and walk with the swing, who is controlling the frequency? I control the frequency, right? So if I can go at a certain frequency that I desire, I am forcing the swing to go with a frequency that I decided. That is called forced frequency. So there's something called natural frequency, and there's something called forced frequency. Now, when the forced frequency matches up with the natural frequency, if it happens to be equal, then the consequence is amplitude will become more and more and more. And that amplitude build-up is called resonance. That amplitude build-up is called resonance. Like, for example, if you sit on a swing and you're not able to reach the floor, you're sitting on the swing and the swing is not moving, right? And if I tell you, all right, start swinging, what do you do? What do you do to start swinging? Kick your legs. Kick your legs. Will the swing swing? No. If we just like pull the ropes, nothing's going to happen. It'll stay there. What should you do to actually swing? You're not going to touch the floor, but you can swing really well. What should you do? Just lean back. When you lean back, your center of gravity goes back, so the swing will start moving forward. As soon as the swing goes as much forward as possible, then push yourself forward. And when you push yourself forward, your center of gravity is now shifted to this side. And when the center of gravity shifts to this side, the swing will return. And as soon as the swing comes here, do that. When it goes to that side, do this. When it goes to this side, do this. And if you force the swing if you force with a frequency which is perfectly in sync with the natural frequency of the swing itself, then what will be the consequence? The amplitude will build up. After every action, the amplitude will grow, and you can actually make it go really, really dangerous. You understand what I'm saying? On the other hand, if you just do like this, like this, like this, with a totally different frequency than the natural frequency of the swing is not going to go anywhere.
Is that like using a glass and making it?
Exactly. Yeah, so if you take a glass and with clean hands and just wipe your hands like that, it starts making that beautiful tone. And that's because the vibration that you are trying to create, one piece of that vibration possibly has the frequency of the cup itself. And that causes resonance. Have you heard about the radio singer breaking the wine glass at the listener's home? The opera singer at the radio station, she's like raising her voice and like holding that pitch up. Now, some other listener at home had a wine glass sitting next to the radio. And apparently the wine glass, when you hit a wine glass like this, it'll give you the ting sound. That opera singer was holding the same frequency for quite some time. So what happened is the wine glass started resonating and it broke. Now some people call it ghost. When something strange happens like that, they say, oh, that's ghost. But a lot of it is physics, believe me. So the wine glass broke at the listener's home. How? The opera singer sang something there. Can you break a wine glass with your voice? Yes, you can. You can try it. All you do is take a wine glass, hold at the bottom, hit it like that, get the tone, scream. Just scream right there, and then this will vibrate. The wine glass will wobble. And if you want to put a straw inside, you can put a straw inside. As soon as the straw starts kind of getting agitated, that is an indication that you are really reaching that natural frequency correctly. You have to hit the tone correctly. If it is like ting, and then you say, oh, it's not going to work. Okay? You have to match it with it. And that is when resonance takes place. And there is a video on YouTube. You can look it up at your own time. It says, kid breaks glass with voice. It's a raw video taken at home. A kid apparently is trying this experiment. There is another kid screaming in the home. There's a parrot screaming in the background. The mom is in the next room. It's a real raw video. And he's not wearing glasses or goggles or nothing of the sort. He's just like experimenting. And then he put the straw inside and starts screaming once. Clears his throat, tries again. Third time he clears, and then does it, just breaks it. The glass breaks, and immediately he says, "Mom, I just broke the glass." And mom comes running, and no, stop. Because the glass is everywhere. It's beautiful. Anyway, so he didn't use any protections at all, but that is possible. All you have to do is reach that frequency. So what is resonance? When the natural frequency is matched with the forced frequency, or when the forced frequency is matched with the natural frequency, the amplitude will start building up, and that buildup of amplitude is called resonance. Now, in your car, do you tune your radio to different stations? Right? You turn a knob or something like that to tune different stations. What is happening over there is resonance. That's called electrical resonance. Because the radio frequency, your radio waves are coming at different frequencies, but you want only one particular frequency. That's what you want. So you can't just let your amplifier amplify everything. So you want to select that particular frequency. That's the station that you desire. So what you do is there is a capacitor and an inductor inside. We actually we turn the capacitance value. And so what happens is there's an electrical oscillation inside the radio, which depends on the capacitance value. So according to your position, it actually has a frequency of electrical oscillation. And when the electrical oscillation frequency that you are setting it here is matching with the radio station's frequency, the electrical signal becomes too strong, and that is getting amplified. So whatever is in resonance is what gets amplified. That's called electrical resonance. What I just told you is mechanical resonance. Bridges are broken in the past because of resonance. You can actually look up later on YouTube the Tacoma Bridge collapse. What broke the bridge? It's a steel bridge. What broke the bridge? Wind. Just wind. The wind was blowing over the bridge and the bridge started wobbling. And that wobbling has a frequency. But the wind was actually like blowing over it again and again. So the wobbling becomes more and more and more. And finally the whole bridge breaks. There was a car left on the bridge and there was a dog in the car. The only casualty is the dog. The professor actually somehow managed to run, leaving the dog behind. He tried to take the dog, but it was too risky to go and fetch the dog. The car itself, like, you know. So it's a video. Watch it. It's actually pretty interesting. That is resonance. So when they make bridges and stuff like that, they make sure that resonance is not supposed to happen. That is dangerous for the structures. Okay, so that's called resonance. Got an idea? What is resonance? What is MRI? Yeah, magnetic resonance imaging. So we're using a resonance technique to, create that image. That's called magnetic resonance imaging. There's NMR, nuclear magnetic resonance. So all those things are related to resonance. So it's a very important concept. So that is what we're going to use here. Now, to demonstrate this concept of resonance, I've got something over here. Now this one, it's a sound box kind of thing. This is a tuning freak. This is the tuning fork. This is a fork. So when I hit that, the prongs are actually vibrating, and because the prongs are vibrating, that vibration is taken to this box, and that's what you're hearing as a sound. So, right? So the frequency. Can I make it vibrate with my voice? Sure. All I have to do is use that frequency right here. You hear anything? I can hear. Still going on. Okay. It is definitely. Let me try on this. Yeah, you got it. Yeah. Yeah, it is vibrating. So this one, somehow I managed to match the frequency, and then that is also vibrating. This is in resonance. So when I hit this tuning fork, everything in the room is vibrating with this frequency right now. This is, can you hear the sound? That's because it is shaking your eardrum. It is shaking everything in the room. It's shaking the projector, it's shaking my laptop, it's shaking the table, it's shaking everything in the room. But everything in the room is not going to start vibrating because this is not able to force everything else to vibrate because the frequencies are not matching. But what if the frequencies match? So what I'm doing is I'm going to keep this here. I'm going to keep this here. And I'm going to hit this. So what's going to happen now? When I hit this tuning fork is going to make everything in the room oscillate or vibrate. The only thing that matches this frequency is that one. So what will happen to that? It will pick it up, and its amplitude will start getting bigger and bigger, and you'll hear the sound coming from that. So right now it is sitting quietly, but you hear the sound right now. I'm going to hit this and stop it. That's what I'm going to do. Is the sound coming from there? Yeah? That is resonance. So I hit this, but the frequency from here disturbed that because it matched perfectly. Okay? And of course, there are other things called beats. If you have heard about beats, not the beats. Yeah, of course, then we use the same word for their great thing. What is beats? Beats is what you're going to hear right now. You hear the ups and downs? Now you will see in theory that it is due to constructive and destructive interference. The waves sometimes support each other and sometimes kills each other. Because these are waves coming to you, like compressions and expansions. So when two compressions come together, you will hear it loud. When a compression and an expansion approaches you, it will like suppress it. So that's called beats. So you hear it up and down. So when you hear this frequency going up and down, that means they're not matching frequencies. Musicians actually use this technique to tune instruments. Like you press a certain key on a piano or something, and you can tune your guitar till you don't hear any more beats. Because if you hear beats, that means the frequencies are not the same. Frequencies are not the same. And the more the frequency differences are, the more the differences in frequency. So that vibration. Yeah, this means the frequency is not matching. So when we tune instruments, we tune instruments in such a way that the beat frequency is 0. That's beats. And the lower the frequency, the closer the frequency. Now remember, everyone is hearing differently. It may be up and down for someone, and for some others it will be down and up, because it depends on where you're sitting. Because the waves are actually coming and merging. So how it merges depends. So you understand the concept of resonance, right? And that's exactly what we're going to do through this instrument. Now, resonance is one way you can now he was talking about a look at this little pen cap. Where did that whistling sound come from? What happened here is this. When I was blowing air above the mouth of this, I was creating a lot of frequency, like disturbances. But one particular disturbance found its way down and up. It reflected. It went down and came back and perfectly in resonance. So every tube has a certain resonance frequency. So when the frequency that matched was that particular frequency. So you heard that sound. Now, if the pen cap was a longer pen cap, like that, it is definitely supposed to give a lower frequency. You see, this was a shorter pen cap. So this was a shorter one, and this is longer. So this frequency is probably, this one's around 3,000 hertz, 3,000 hertz, which is 3,000 times per second. And this one is probably around 2,000. She's closing. That's 2,000. And this one, that is around 3,000. Okay, so why is it happening? So this one is supposed to be much lower. At the front, okay. So what is happening is that frequency The disturbance is going down and getting reflected, comes back up again, and that is how it produces a standing wave. And again, you will hear me speak all these things in the chapter videos. I know you're fed up with my voice, kind of monotonous voice through all those classes. I can't help it. I wish the classes were lively like this, right? So you can actually like see. And the other one is, well, I could have made it a little more interesting, but it was so difficult when I'm sitting in front of a computer and trying to record stuff. I'm kind of talking to a blank wall, you know. If at all one person was sitting on the other side and I can actually like interact with that person, then it would be a totally different story. Like right now, this is being recorded and I'm not even looking at it. So therefore, I'm actually like talking to you and I'm sharing stuff with you. All right, so this has a natural frequency, which is what you're hearing right now. And these tuning forks have different frequencies. This one has got 1024 hertz. And this one has 341 hertz. Now when I look at a tuning fork, one student's aim of the experiment is to determine the speed of sound in the lab at room temperature. So speed of sound at room temperature and at 0 degrees Celsius. That's what you're supposed to be doing. What's the materials required? Materials needed. You need tuning forks. So I'm going to use two tuning forks, 512 hertz, and I'm going to use a 512 hertz and
Did you say 512 or 512?
512, 512. This is C. This is a C in music. That's a C in music. And this is 426.7. 426.7. 426.7 is the next one, which is A. That's A. If you are musically talented, you will be able to hear this and say, yeah, that is A. I'm not that. All right, so this is A, and that is C. So 512 and 426, these are the two tuning forks we are going to use to study this. So two tuning forks. We need the resonance column. We want water to be poured into that tube. So what is a resonance column? The resonance column is basically a tube that is connected to another rubber tubing. And the rubber tubing is connected to a reservoir. So this is a reservoir where you can actually pour water. And whatever level of water you pour in here, these two levels are going to be matched up. So if I lower the reservoir, then the level of the water will come down. Get it? If I lower the reservoir, the level of water will come down. If I raise the reservoir, the level of water will go up. So basically, this is the level of water that we are trying to look for in a resonance column. What else you need? You need the tuning fork, you need the mallet, and you need the water resonance column, and the thermometer that we're going to use, thermometer. That's it. Okay. So now comes to the theory. What's the theory behind it? The theory behind it is this: that when you have a tube like this, when you have a tube and suppose you have water level at this point, whenever there is a disturbance that is created on the top, the wave is going to go down and reflect and come back. And this distance from here to here is actually 1/4 of a wavelength. The symbol is lambda. Now you will learn all these things through the theory. Okay? So this is lambda. It's called wavelength. So what is a wavelength? This is one wave. And a standing wave is basically this. This is one wave. This is one complete wave. This is called a node, node, node. This is called an antinode and antinode. And if you watch the videos again, you'll see demonstrations of all that stuff. I have included demonstrations in the video, in the class videos. So you will see all that stuff. The distance from here to here is the wavelength. That distance is called the wavelength lambda. Lambda is a Greek letter. Lambda is a Greek letter. So this is lambda from here to here. And from node to node, the distance is 1/2 lambda. And from a node to an antinode, it's going to be 1/4 of lambda. This is an antinode, and this is a node. Now, the other issue is the antinode is formed always slightly outside the tube. The antinode is formed slightly outside the tube, like this. And that is called the end correction. So the lambda over 4 is the end correction included. So if length L1 is this length, L1 plus end correction is lambda over 4. Now, since end correction is something that we have no idea of course the end correction depends on the diameter of the tube. But since we don't have much idea of end correction, we will have to repeat this experiment one more time to get the third resonance. So, I'll remove this. We will try to get another resonance length, which is going to be almost here. So when the water level is this way, you will find the wave set up like that. So if it is coming to resonance here, it will come into resonance even at this point. So how many wavelengths are there here? So the antinode is again formed outside. The antinode is formed slightly outside. So the distance from here to here is 3 lambda over 4. 3/4 of a lambda, that's from here to here. Make sense? That is 3 lambda over 4. So if this length is L2, our equation is L2 plus E is equal to 3 lambda over 4. L2 plus E is 3 lambda over 4. Now we have two equations, systems of equations. If I subtract these two equations, guess what? I can get rid of the E. So that's what I do. I subtract the first equation from the second equation, so I get L2 minus L1 is equal. What is 3/4 of lambda minus 1/4 of lambda? What is 3/4 of a quarter? What is 3/4 of a dollar minus 1/4 of a dollar? What is 3/4 of a dollar minus 1/4 of a dollar?
50?
Huh?
50?
Yeah, half a dollar. Normally when it comes to dollar, everyone gets it right. But in terms of lambda, no. So 3/4 of a lambda minus 1/4 of lambda is half a lambda. So see how we got the end correction out of the picture? So that's pretty much what we're going to do. So this will help you to find the lambda. So lambda is equal to 2 times L2 minus L1. This is the way we are going to find out the wavelength. Now what is our equation for velocity of sound? It is frequency times lambda. That is our equation for velocity of sound. Frequency times lambda. So what frequency am I using to get this resonance? That is F. So F times lambda, and what is lambda? L2 times L2 minus L1. So our final equation for velocity is frequency times 2 times L2 minus L1, and then times the frequency. So this is going to be our equation for finding out the velocity of sound.
Is that the part we need to put on our lab report, or do we need to put like everything?
That is the most important thing that needs to go on the lab report. This one.
Okay.
This is just for your information of what it is. And this is what we are actually going to do. So what I will do in front of you is I'll find L1 and I'll find L2 when it's resonating, and then you can do the rest of it. So let me give you the table for our work. The table for our work is this. The first one is frequency. What frequency are we using in hertz? So we're going to use 512 hertz. And we're going to use 426.67. We're going to use these two frequencies. And our first resonance length is L1. And we want to write it in meters. Our second resonance length is L2, which will also write in meters. And then we will find the lambda by doing 2 times L2 minus L1. And then we'll find the speed of sound by using frequency times lambda. So this is going to be meters. And this will be meters per second. And we're just going to do it 2 times, and then you're done. So that's the table. All right, let's see. So I'm pouring water into this. Hopefully it's not going to leak much. So on the resonance column, you can see there's a scale which will let me read the length straight away. So I'm taking this tuning fork, which is 512 hertz, and we'll start off. So what I do. You can hear the amplitude change. But it's not good enough, so I'm going to bring it down. I don't know where it's going to be good. I don't know if this is the highest. I think we crossed it, or maybe not. Is it getting louder? It has to be the loudest. That's when we can take that length. Louder? Let's go down a bit. This is 15.6. Let's see. I'm going to go down a bit and see if it is going to increase. No? I think we got it earlier. Let's go to 15.5. Yeah. Louder? That's 15.5. All right, take it as 15.5, 15.6.
For L1.
15.6 centimeters. So what do you write there? 0.156, because you're supposed to put it in meters. So for L1, put it as 0.156. Is that okay? Now I want to find out the L1 of the other one. It's easier to do that way. So let me find the L1 of the 426.67 hertz. Obviously it's not in resonance, so I have to get it in resonance. So I have to go down. Because this is the lower frequency, I need longer length. I think we skipped it there. So right around there. So it's around 18.5-ish. It's in one way good that only one person is doing it, because there'll be a lot of howling otherwise. Oh, I think we skipped it. Let's go a dash lower. Let's see. Better? All right, we'll go with this 18.9. 18.9. So right on this, right for 426.6, right 0.189. Now we will go down to the next level. leaking a lot, but it's all right. So this is 512. So what was it, 15 point something? So it should be around 45-ish, around that area. So let's wait. It's around 49, but let's try again. No, I think it's gone down. I don't know which one sounded louder. Louder? Loudest to you? Okay. It's 48 point. 48.6 is it? That is okay. Okay, 48.4. So 0.484 for 512 hertz. 0.484. Can you do the calculation now? Because I got both the lengths now. So can you fill in the next column? Lambda equal to 2 times L2 minus L1. So just find out what it is. And fill up that, and then fill up the last column, which is supposed to be speed of sound at room temperature. So that is the answer that you're supposed to get at room temperature. Should be around 24 degrees Celsius. So at around 24 degrees Celsius, you should get, to my estimation, it should be around 340 something. What do you get? What do you get as the last answer? Around 342, 341, 335. Also depends on the temperature of the water. It's probably not the room temperature. So yeah, the speed of sound changes according to temperature. 335 you said? Okay, write it down. Now we'll try to go for the second length of this. What was the first length?
18.9.
So it should be around 3 times that, so around 54, 55, 56. Around there. This is 426.26, so 426.67. The 512 we have already done. Nine-ish. Looks good. That was 50. That's better. I'll go with this, maybe 59.3. So 0.593. 0.593. So now we'll do the calculations. 0.593 is L2. How much? 344.75. We'll take it. We'll take the average then. Yeah, so you got 344 point whatever, and then you got the other one, and then you take the average of those two. That I think cancels off our errors because we are getting 340 then average.
What is the point, like when you're adjusting the reservoir,
Mhm.
like what's that called? Like when you're finding like the right length, is it just like,
Over here, that's
Yeah.
called the resonance length.
oh,
Yeah, that's the resonance length. Yeah, the temperature is 24 degrees Celsius. So yeah, what did you get as the average of those two?
.340.31.
340.31. That is the speed of sound. That's the speed of sound that we got. So we got 340.
340.31.
Okay, we leave it as it is. This is at 24 degrees Celsius.
How did you get that? 340.31?
The average of those two numbers that we got here. Remember, we got 335 something here, and then we got 344 something like that. You take the average of those two. In fact, if time permits, we could actually do more and more tuning forks and take more trials and take a better average. That will come much better. Now, instead of using our ears only for finding the resonance, we can have a microphone attached to it, and then we can check the level going out and maximum level. You know, we can actually do many things like that to get to know whether it's resonance or not. because on the graph, on the oscilloscope, you can actually get the peak really shooting up if it is really resonance. So we can do all those things, modifications, if you want to really get more close to the right answer, but that gives you an idea. So this is the speed of sound at 24 degrees Celsius. Now what is the speed of sound at 0 degrees Celsius? That's what we're trying to find out. So to find out that, what you need to know is how is the speed of sound affected by temperature? For every 1 degree Celsius change in temperature, the speed of sound changes by 0.59 meters per second. Like if the temperature goes up, this one goes up. So when for every 1 degree Celsius temperature rise, the speed of sound rises by that much. Make sense? So based on that, what do you think is the speed of sound at 0 degrees Celsius? So what we're going to do is, the temperature from 24 to 0 is 24 degrees Celsius fall. That means what is 24 times 0.59? That much is the speed of sound changing. So 24 times 0.59, whatever it is, how much is that? 14 point?
14.16.
That much is this one going to go down further. So that means what is the speed of sound at 0 degrees Celsius? Subtract 14.16 from here. So you get 326 something.
326.15.
Yeah, something like that. So 326 approximately at 0 degrees Celsius is the speed of sound at 0 degrees Celsius. It's supposed to be around 330. It's technically around 330. Now I know why it is coming out wrong is because our measurement here was not appropriate. That's why we got 335, right? If that was done correctly, the next one was correct, 344, that was correct. Because if it was 344 and subtract this, you'll get exactly 330. Make sense? So apparently that first reading was not, there was some error. So maybe the second resonance length that I got was slightly off.
You said it should be 330 at 0 degrees?
Yeah. It's supposed to be at 330. All right, so this concludes this experiment. We have done 8 experiments so far, right? And then last one was an electricity experiment, which is only one experiment. We'll do it when we come, I don't know which day it is. And we'll just do that one experiment and we'll be done. Precautions. Now these things can change their frequencies if these are dropped. So make sure that it is not dropped. Make sure we don't touch that with the resonance column. Make sure that make sure the amplitude is the loudest when you're actually measuring the lengths L1 and L2 and all that. That is what represents the resonance. Resonance is the maximum because you start hearing the sound long time. So for a good range, you'll actually start hearing the sound. But when is it actually the highest? That is a decision that we have to make. And this apparently is kind of leaking all the time. So the level is actually falling quite rapidly. So there's a lot of water on the floor. Be careful. And because of that, probably we have more errors, right? Because by the time we actually oh, the sound is correct. And then you're already checking there is already level is going down. So that's possible. That's it, and that concludes it. So the speed of sound at room temperature we found out to be approximately 340, and then we found out that the speed of sound at 0 degrees Celsius apparently is supposed to be 326 meters per second, which is supposed to be 330. And complete your lab report with these things, precautions and conclusions, and that's it.